So without further ado, we will now hear from two very excellent speakers on the current landscape and near-term development at a very critical intersection of quantum and AI technologies. First, Dr. Stefan Lacheneur, Vice President of Engineering and Lead Scientist at Sandbox AQ, will present on AI-integrated quantum sensing applications. And then Dr. Caitlin Jones, Senior Researcher at the Quantum Software Lab of the University of Edinburgh, will share insights on quantum-enhanced AI and machine learning. So, Stefan, I will first give you the floor. So please feel free to present your slide whenever you can.
All right, great. Thank you so much, Wenting. Let me share. Okay, tell me if that doesn't come up. So thank you for having me, and thank you to all the participants for joining to listen and to learn. This is a very exciting time and a very exciting topic. I'm going to focus on quantum sensing and its relation to AI and the convergence of these technologies and the applications that they're going to open up. I promise that this will not be a technical talk. There won't be, I won't focus on any kind of technicalities. There will be a couple of slides that contain some technical information, but I will tell you what kind of messages you're supposed to get from those slides. Just general high-level messages. First, a few general comments. Let me advance the slide. So quantum sensing is, I think, an underappreciated aspect of quantum technology. As we'll discuss in a second, a lot of the underlying hardware that is used for quantum sensing is the same as that is used for quantum computing. It's all the same kind of stuff underneath. It's this new era of quantum technologies where we have enhanced control over quantum systems. Quantum, this is the year of quantum. Quantum's been around for 100 years, but why are we excited right now about quantum technologies? It's because in the modern era, we have unprecedented control of very, very detailed systems, which allow us to do interesting things. And one reason to be excited about quantum sensing, as we'll see, as opposed to other aspects of quantum technology like quantum computing, is that quantum sensing is available right now. Like right now, there are modern quantum sensors that can do very interesting things, unlock new application areas, which I'll touch on in a minute. And indeed, there is decades of progress ahead of us as quantum technologies as a whole progress, and the more things like scaled quantum computers and so on come out and do the interesting things that they're promised to do. And quantum sensing will also advance. But one thing I want to emphasize is that quantum sensing today can already do things. So what can it do first at a high level, and then into and then into a couple of specific applications? Basically, what we're doing with quantum sensors, what is the quantum adding to it? At the end of the day, even though I say quantum sensor, it's a sensor, which means it's detecting a thing. So there's some small, for a very sensitive detector, there's a very small signal that I'm trying to detect, and say a tiny change in temperature or a tiny fluctuation in a magnetic field or an electric field. And what the quantum effects allow me to do is have higher sensitivity to those things, and in general, better operating characteristics than old school non-quantum sensors. Quantum itself is not magic. And in fact, there are what I would call old school sensors that take advantage of quantum effects. Think about something like an MRI machine. That is in a way a quantum sensor, but it's big, it's expensive. It's an old style quantum sensor, non-mobile. New kinds of quantum sensors, the ones available today, they operate on principles very similar and in a lot of ways the same as an MRI machine for certain areas, but can be small, portable, cheap, and operate not in a special room somewhere, in a research lab or deep inside of a hospital, but out in the field doing interesting things. And maybe one more general comment about the relation with AI before I go on. As we'll see, AI, the modern revolution in AI, and not even necessarily large language models. AI is bigger than large language models. When it comes to sensors, these are not language machines. So language models are not necessarily the way to unlock their power. But modern AI enables these sensors to operate in the way that they operate, and I'll say how. But also going the other way, having what these sensors do for us is they enable new kinds of information, us to gather new kinds of data that we could not previously gather because of the enhanced sensitivity, the better operating characteristics. And that data feeds into the next generation of AI models to really unlock the applications that we want to unlock. Okay, so as we move on, another general slide. One message here. There's no, on the left side, you'll see a list of different kinds of technologies. There are two messages here. One is there are all kinds of different quantum sensors, and there won't be just one single winner. They all have different operating characteristics, are useful for different things. No one technology underneath, no one piece of hardware will dominate for all applications. The other thing to recognize here is that the list of technologies, it's the same list of technologies that you would use to build a quantum computer. So the set of technologies is in common. It's just quantum technologies. But here we're doing sensing applications, right? We're not trying to isolate the system to have it do a computation. We're trying to expose the system to our environment and detect tiny changes in the environment and then do something with that. The kinds of applications this unlocks are vast. And here and from now on, I'm going to focus on magnetic sensing. So I want to detect tiny changes in the magnetic field. Magnetic sensing is one of the oldest forms of sensing. When we use a compass to tell which way is north, that's a kind of magnetic sensor. It's detecting the magnetic field of the Earth. And that's a relatively big magnetic field compared to the ones we're talking about here. So just to highlight a couple of things. So if I look at something like chip cybersecurity or chip failure analysis, what I might imagine here from a magnetic sensing point of view is that the electronics, as they're running, are generating tiny magnetic fields in the wires. And if you had a very small magnetometer that could fit into a microchip and detect wire by wire what the current was doing, you would be able to tell, hey, is this microchip actually operating the way it's supposed to? Is there any rogue circuitry inside? I'm not sure. Let me just check. Let me test it for real with an independent test. And such a magnetometer that has that nanoscale nanoscale resolution, but also the sensitivity to detect those tiny magnetic fields, that's the kind of operating characteristic that is enabled by quantum technologies, modern quantum technologies. So I'll come back to some of these other applications in a second. Here's one more general slide. This is the most technical slide, but I promise you don't have to understand all the technicalities here. There are a couple of high-level messages that I want to show. So one is all the different icons, again, represent all different ways you could build, in this case, quantum magnetometers. There are many different modalities, many different pieces of hardware. And the message of this slide is that there are different locations on this graph just illustrate all the different operating characteristics. Okay, so again, there won't be a single winner. Different kinds of technology operate in different regimes and are useful for different applications. So for a given application, the first thing you would do is look at a graph like this and see, okay, which kind of technology is best for my application? And there are many other things to consider besides sensitivity. Sensitivity is what's being measured on this graph. The other thing to notice about this slide is the vertical axis. It's a logarithmic axis. So as you go down on that axis, the signal is getting weaker, exponentially weaker, that you're trying to detect. and background noise. So I remember the compass, which is detecting the main Earth's magnetic field generated by the core of the Earth. How big is that on this plot? Well, it's like basically at the top or slightly off the scale. And so what the things that we're trying to detect are very, very small compared to just natural magnetic fields that exist around us. And that means the signal to noise ratio is a major issue. And there are two ways to deal with that issue. One is to take your sensor and try to isolate it from the environment, put it in a very clean space, put shielding around it. And that's a traditional way of making sure that the background noise doesn't get in the way. But the modern way to do it, and this is where AI comes in, the modern way to do it is to do that at the software level. Okay, so one of the major problems, one of the things that is really enabling quantum sensing today is the use of AI and software signal processing in order to reduce the background noise, which is much bigger than many of the signals we're trying to detect for the applications. Reduce that background noise to the point where you can actually get something useful out of your very sensitive detector. So this is that interplay between AI and quantum sensing. So those are the general comments I wanted to make. Let me focus on one or two applications. The one I want to mainly talk about is the navigation piece. And again, even within navigation, there are many different ways that people talk about navigation using quantum sensing. But I want to focus on, because I like magnetic sensing, it's what we work on at Sandbox, it's what I'm most familiar with. I will talk about the problem of navigation using magnetic quantum sensing. And I've already kind of hinted at this application when I talked about the compass. Okay, which way is north? That's, ancient magnetic sensing for navigation. But in the modern era with modern sensors, we can actually do much better in a way that's kind of surprising. I think I don't have to tell this audience that this is a major concern. Most navigation positioning these days is done via GPS or similar systems that rely on satellites. And not only are the satellites very vulnerable themselves in the case of, say, large-scale conflict, those satellites won't last long. But the because the satellite is remote and distant from yourself as you're trying to navigate, it can be interfered with. Your connection with the satellite can be interfered with, the signal can be spoofed, etc. And this is an increasing issue, especially in the conflict areas around the world. But we can do better. We can do better without relying on a satellite, without relying on any kind of external system, just within, say, our aircraft as we're flying around. There are a few ways we can do better, and one is magnetic navigation, modern magnetic navigation. So the way this works is, this combines data and sensors and algorithms, okay? And so I'll go through that in a second. So first, the data. What is the data? So beyond just the standard always points north magnetic field of the Earth that we've been detecting with compasses for a long time, if you look at how the tiny changes in that magnetic field, it varies a little bit based on the rocks, the particular minerals, the mountain ranges across the Earth. If you could detect tiny, tiny changes, like 1 part in 1,000 kind of changes in that magnetic field as you move from place to place, you would effectively have a map of the Earth. And it turns out, here's a picture of it, right? Here's a picture of it here. It turns out that map, it's almost like a fingerprint for the Earth. There's enough data there where if you could collect it in real time as you're moving around, you could tell where you were anywhere on the Earth. And this is how certain birds, for example, navigate as they migrate across the Earth. They have magnetic sensors in their heads that tell them where they are, basically. How do we do this? Well, we need a sensor, number one, that's capable of detecting those tiny differences. That's where the quantum sensor comes in. And those quantum sensors exist today. They're ready to go. Number two, we need these maps. The map, well, you've got a picture of one of those maps here. You can always have better maps, but for the most part, the maps exist. at least starter maps. We can make them better over time. And then you need the AI and the algorithms in order to take the raw signal from the quantum sensor, remove all the background noise, because remember, we're out in the field, we're not in a clean lab environment. So there's a lot of background noise, not just from the Earth, the big magnetic field of the Earth, but also all the electronics in our airplane, say. We need to screen all of that out, not using physical shielding, but using software. And then we need to take that now clean signal and turn it into a positioning result, and that's more navigation algorithms. So there's software pieces, hardware pieces, and you could, in principle, use this to tell where you are all by itself. In practice, that's not even what you would do. In practice, what you would do is you would use a combination of systems. For example, for those of you who know more about this kind of topic, there's another kind of navigation device you could have in yourself, essentially a gyroscope, inertial navigation system that tries to compute where you are based on your velocities and your accelerations. But the problem is those kinds of systems, if that's all you had, they would drift over time. And the longer you went without some kind of anchor, which usually comes from GPS, you would end up very far off course. And so something like a magnetic navigation system, even if you're not using it exclusively, you can use it to anchor something like your INS, which every aircraft already has. And this effectively turns any INS into a very much higher quality navigation system, if you want to think about it through the INS lens. There are other methods that you could use for navigation, visions, you could look at the stars, etc. And these all have different operating characteristics. The point here is any one of them is not a perfect system, but together, right? But together they can really solve this this problem of GPS denial and or GPS spoofing by bringing in a collection of technologies that can operate without external some kind of external resource like a satellite. And the magnetic navigation enabled by quantum sensors and AI is an important piece of that puzzle. So again, this slide doesn't contain anything new. It just illustrates again how we can go from raw signal through some software processing into a position estimate of where we are. And finally, I'll just mention for this application that, again, this is like a real thing. It's not just theoretical. The sensors exist, the software exists, and you can actually fly like this. We've put in thousands and thousands of miles, over 100 hours, meeting requirements for navigation requirements without GPS using this kind of system, and it's ready to go now. And we at Sandbox plus others around the world are like using these kinds of systems in practice, and in a few years they'll be commonplace, and this kind of problem will be mitigated. In the interest of time, I won't spend a lot of time on this next application. I just wanted to mention it as another application of quantum sensing with magnetic fields. This time, it's magnetic fields coming from your body. As your body, as your heart beats, it generates electrical signals that you measure with an EKG. It also generates magnetic signals along with those electric signals that you could detect in principle, but they're very weak. And so again, the same kinds of quantum sensors can enable you to make a magnetic map of what's going on in your heart as it's beating. And this magnetocardiography is a complementary signal to the electrocardiography and can actually enable, it can actually provide actionable information in ERs, in emergency rooms, when people are having heart attacks. This is it's a known thing from a clinical point of view. The only problem is the lack of a sensor, which is sensitive enough. The only problem in the past is the lack of a sensor, which is sensitive enough to detect the signal, and some kind of way to eliminate the background noise. Because in a busy ER with a lot of equipment around, there's a lot of electronic noise. And those two problems are solved by quantum sensors plus AI, as I've said. So this is another technology. Here's an example of a prototype machine. It exists. We're testing it in hospitals right now, and it will, well, it's another thing that will become commonplace over the next few years. So I think I'm basically at time. So I'll stop there, and thank you for your attention.
Thank you so much, Stefan, for the fascinating presentation. And I especially appreciate your effort in, making the presentation accessible and less technical. I imagine that's quite different from, the usual requests you get in the tech industry. So thank you so much for the effort. So it's really encouraging to know that, quantum sensors are already a reality. Which is different from some other quantum fields, especially quantum computing. And I also found it fascinating to hear about the concrete use cases you just presented, especially those that are very close to real world applications. And also things were highlighting, how AI can enhance quantum sensing capabilities in those real world scenarios, particularly the role of AI in reducing the background noise for detection and monitoring. I can already see, some potential crossover for, with the military applications, which will be really relevant for the international security discussions. So thank you so much for the presentation. And now I would like to hand over to Caitlin.
Hi, good afternoon and good morning, everybody. Let me just share my slides. I've now gone full screen, so I can't see the web seminar. Could someone just confirm that you can see my slides?
Yeah, it's working well. Thank you.
Okay, perfect. So yeah, thank you very much for having me to talk about this exciting topic. Yeah, and nice to also talk about it with someone who's just spoken about a different aspect of quantum enhanced technology, quantum sensors. I am going to be talking about a field called quantum machine learning. So this title, Quantum Enhanced AI and Machine Learning. Just to note, throughout this talk, I will probably interchange the words AI and machine learning, because for the purposes of quantum machine learning, many applications and topics can be basically used interchangeably between AI and machine learning. So if you hear me using both phrases, this is why. So yes, I work at the University of Edinburgh on this topic, and my background is a physicist, but I've also worked a lot in data science and AI, which is kind of how I've come to this field. So today, I'm going to be hopefully also keeping it at not a super in-depth technical level, with the caveat that if there are technical things on the slide, I will give kind of the main highlights and messages. And I'm first going to be talking about an introduction to quantum computing. Very sorry if there's background noise. So give a whistle-stop tour to introduce what quantum computing is, and then explain what quantum machine learning is specifically, before then talking about why people are interested in it, how it's different from the status quo of what we currently have in machine learning, and then some challenges and sort of a status for the field. So to kick off, maybe some of you have heard of quantum computing. It's a relatively hyped topic. And essentially what it is a new form of computing technology that exploits the underlying physics of microscopic particles that behave in a quantum mechanical way to perform calculations more efficiently than classical computers. So when I say classical computers, these are the typical computers that we use every day, your laptop, your phone. These are silicon-based devices using transistors. So this is what classical computers are, and quantum computers differ from this by using properties of superposition and entanglement. What are these terms? So if you look at this picture on the top right of my screen, in a classical computer, you have a bit, which can be either 0 or 1, and all the data stored in your computer is stored in this 0 or 1 bit form. Quantum computers differ because in them, the core item is a qubit, which instead of being either 0 or 1, can it be any value, a mixture of 0 or 1, and kind of any value on the outside of this circle, basically. And this is what superposition is that they don't have to just be in a 0 or 1, they can be in a mixture. And then if you combine multiple qubits, so this is a picture of one qubit, if you combine multiple qubits together, this leads to this property called entanglement. And entanglement is a type of correlation between qubits. And this is the core thing that is exploited for more efficient calculations. When I say more efficient calculation, what that means is the same task that a classical computer would do, a quantum computer can achieve in far fewer steps. Some tasks have been shown that this is the case. So that's what efficiency means when I use that in this context. So quantum computing is a relatively young field. So it was in about 1982 when the physicist Richard Feynman first proposed quantum computers with the idea of using a quantum computer to simulate physics. So the idea is if you have a quantum phenomenon, then you could use a quantum computer to simulate that quantum phenomenon more efficiently than a classical computer could. And then another famous landmark in the field was in 1994, there was the famous Shor's algorithm, which is a factorization algorithm, which is sounds like quite a dry mathematical topic. But the reason that it kind of gained a lot of attention is because it has quantum advantage, meaning it can be shown to be more efficiently done on a quantum computer, and it can be used in cracking certain types of cryptography. So, for example, RSA, famously. So that was all kind of theoretical. In around the year 2000, the first multi-qubit interacting qubit quantum computers started to come online, and more and more developed. And then in 2018 or 19, depending on how you count it, the Google company published a paper showing a practical demonstration of what they called quantum supremacy. There's still some controversy in the field about if this could be considered supremacy, but they accomplished a task that they said could not be accomplished in a realistic time span on a classical computer. I'll talk in a little bit more detail about what they accomplished later. And the field has continued to progress since then. So, for example, a recent big development in 2023 was that some scientists led by Harvard demonstrated what are called logical qubits, and these are more robust and scalable qubits. That is what we're going to need for like widespread use of quantum computing at a practical level. So this is kind of just a one-slider to give you an idea that quantum computing is a technology basically that we hope to accelerate classical computing. One thing I kind of haven't mentioned is I said, it uses these microscopic particles with quantum properties to achieve this acceleration. What are these microscopic particles? And actually, there's many different types of microscopic particle that people use. So this is just a few of them on the screen. This is by no means exhaustive. So people do use superconducting qubits, trapped ions, neutral atoms, and photonic qubits. And so the pictures here on the screen are of real quantum devices from various different companies that have produced these quantum computers. And these are all at different scales, so different numbers of qubits, I would say different levels of technological readiness. And I think this is important to emphasize that these are all really different devices, and there's so far no consensus or, to put it colloquially, like winner in the field. Like if you think about classical computing, we have like silicon-based devices that use transistors. Like every single computer essentially uses this, and it's just totally ubiquitous. Whereas for quantum computers, we're not at that stage yet. There's still many different competing devices in competing also regions of the world, even for these different types of quantum computer. Okay, so that's my brief introduction to quantum computing. I'll now talk about quantum machine learning. So this term is very broad, And essentially, it's anything where you are using a quantum computer to assist with some part of a machine learning task. So it could be used as a subroutine to assist with the machine learning task, with obviously the goal of giving some acceleration or some quality improvement over just a purely classical process without a quantum computer. So I put a little picture on the screen here to demonstrate what that might look like. So you can, you could input your data, and this could be any type of data that you would currently use, for machine learning. So it could be image data, text data, some mixture. It could be images. There's no, restriction on that. And then you could do some classical pre-processing. So you put it into a classical computer before handing it off to a quantum computer that does some or all of the calculation that you're interested in, and then you get a result out. So this is a really simplistic picture, but the reason I've included it is to emphasize that the input and output could both be things that are currently used and commonly used in the field. So it doesn't mean that you have to completely, reinvent all the data sources and all the outputs that we might be interested in. Quantum computing aims to be able to have be a part of a subroutine that accelerates existing computing. So why is this important? Because if you think about all the different possible applications of machine learning, and I'm sure with ChatGPT and all of this hype, people are very aware that there's many things outside of text-based models as well. Quantum computing potentially could be involved in all of these because it's like an accelerator technology. So that's the kind of message of this slide. I'll also note this is not the only architecture that I put on the screen for quantum machine learning. This is just quite a common one, and I think one that makes my point. So here's a bit of a real-world example to show that people actually are doing quantum machine learning. So this example actually comes from physics. This is about data that comes from this picture in the top left-hand corner, which is a very cool detector detecting a type of subatomic particle called a neutrino. And people are interested in this for kind of fundamental physics reasons, but they're very hard to measure certain dynamics in this fundamental physics level. And people want to use machine learning and quantum machine learning to help them understand this dynamics. And so what they do is shown in this picture on the right here, is they have this event detection. This is this input data. You can think of this as input data. Then they have classical pre-processing before plugging it into what these things are, QPUs, which stands for quantum processing unit. So this is the quantum subroutine before handing it out again to get some kind of classical result, their solution. So they actually did this on a quantum computer. They used IBM. The IBM company has a quantum wing that builds quantum computers, and they use their Eagle processor to do this task. And although this is, for theoretical physics, I wanted to show that it is used in the real world. You can do experiments. What isn't necessarily true is that you can definitively show quantum advantage, meaning that you can't necessarily show for this kind of setup that the QPUs achieve something that you would not otherwise be able to achieve with purely classical devices. We're still in a phase where we're figuring out which applications are going to be the most enhanced by quantum machine learning. So yeah, this is a real world example. I'm just going to briefly touch on this of why we think there might be an advantage. So unlike, for example, for Shor's algorithm, where we have like a mathematical proof that there is quantum advantage, for quantum machine learning, we don't have such a general mathematical proof for the whole field. We have a few reasons, and one of which is that quantum computers are inherently probabilistic, and they create probability distributions very naturally. And many machine learning tasks are actually the task of learning an underlying probability distribution that you're trying to sample from. Another reason that they might give advantage is better generalization. So generalization is where you are looking at how well a machine learning model can predict from unseen data, and there are some mathematical proofs that give you a guarantee of how well quantum computers can do this. And this is very important because if you want to deploy an actual algorithm for real life use, you know it needs to perform well on unseen data, and you want to know what your error is going to be for how it's going to perform on this data. And some quantum machine algorithms can help you with that. And then the final one, and this is probably the one I'm most excited about, is model compression. So for some reasons to do with the what's called the expressivity, which is how capable quantum machine learning models are at learning distributions with a certain number of trainable parameters, they might be better than classical computers at learning large, complicated distributions with smaller parameters. So this is compressing a model because you can do the same thing with a smaller model with a smaller number of parameters. And if you look in the sort of trend at the moment in AI and ML, where we're having these larger and larger models that often require billions, even trillions of parameters, for the largest models, which have huge data center, energy, water costs, like land footprint costs. And there's already pushback and discussion about this because although people like these devices, they ask, is this sustainable? And quantum machine learning might be able to help by compressing these models whilst achieving the same or better quality of results by utilizing this quantum property of expressivity. So this is a little head-to-head to summarize a little bit of what I've said about quantum versus classical machine learning. So classical machine learning is a mature industry, whereas quantum is a young industry. And so we don't know everything that could have come out of it yet. Yeah, as I just mentioned, in classical ML, lots of large-scale AI models require huge numbers of parameters. This isn't necessarily needed for quantum ML. There's a potential for smaller models, and there's lots of both empirical and theoretical research backing this up. And then one other thing I want to point out is that this is parallel processing for large data sets. So in conventional machine learning, we're very used to be able to use big data and upload thousands or millions of data points pretty easily to our model and process that by parallelizing it over a large number of machines, for example, and doing all the analysis. There is actually a bottleneck at the moment in quantum machine learning where it's actually harder to do this. It's harder to do this parallelization. And this is a problem that needs to be solved, I would say, in the field, because without being able to do this, if you can't ingest the data, you can't train your models well, right? Data is king in machine learning. So this is a kind of outstanding problem in the field. I will just touch on a couple of high potential application areas, in my opinion. So one of which is generative modeling, which is learning an underlying distribution and sampling from it. Like the large language models use generative modeling, for example, as a very important subroutine, and it has lots of different applications. The Google quantum supremacy paper that I mentioned before, their claim was for generating a classically hard to generate data distribution, and they proved that they could do that. Their distribution they used was a bit artificial, so we're still looking for real life, practical, useful distributions, but there is a lot of hope here. The other thing that I would mention is chemistry and healthcare applications. So things like molecular dynamics, which are governed by the rules of quantum mechanics. There's evidence that they can be more efficiently, i.e. with fewer steps, faster, simulated by quantum computers. And this can have lots of applications also in the pharma and healthcare space. And then actually, I'll mention this other one, which is, I think, probably very important, which is unknown unknowns. As I've hopefully emphasized, this is a very young field. And if you compare it to the field of conventional computing in like the 60s and 80s, at that time, we probably couldn't predict all the things that would, what the classical computing would be used for and all its possible different applications, certainly not the machine learning applications. I think we're probably at a similar stage in quantum machine learning, where although, we can point to some early, maybe lower hanging fruit that we can benefit off, it's still a young field, and it's hard to run many algorithms because we don't have very large quantum computers yet. But this is likely to change, and we'll be able to address a far wider variety of potential applications. This is my last substantive slide, and this is essentially talking about the challenges and the sort of status that we currently have for quantum machine learning. So I split this into hardware challenges and software challenges. So hardware challenges, these are these actual physical quantum computers, like the ones I showed on the slide earlier. So one of them is device size. So this is how many qubits we actually have. Current machines, kind of commercially available machines, range between about 5 to 1,000 qubits, which is not very many if you compare that to, like, any mobile telephone. There's far more bits than this, right? So we need to scale up our machines. Another hardware challenge we have is noise. So qubits are fragile, and they can be very easily disturbed by their environment. So, heat, vibration, things like this. And this environment leads to noise, which destroys the quality of results. So we need to be able to protect our qubits better from the environment, or build up something I mentioned before, logical qubits, which are more robust to the environment. This is still ongoing work. And then the final hardware challenge, I'd say, is clock speed, which is how quickly a single computation can be performed. So depending on the type of quantum computer, this can range a lot. So the slowest is about 1 hertz, 1 per second, and then the fastest is about 1 gigahertz, which is, compared to classical computers, they have clock speeds of around 1 gigahertz. So this is a challenge, because if one of the slower devices, even if they need fewer operations to achieve the same task, if their operations are slower, then it's still hard to have an overall quantum advantage. Then for the software side, I would say that the biggest, one of the biggest challenges is that we don't yet know how to check that there is practical advantage for a quantum machine learning algorithm. We don't know how to predetermine if a task is suited for quantum machine learning. And so we have to do a lot of empirical testing, or sort of heuristics. And it would be great if we had a mathematical structure, some proofs to know, like, okay, this is a task that we should use quantum machine learning for, or we should not bother, right? This is, if you think about using something in the real world, you want to check it's going to work before you've actually tried building a model around it. And then the other thing is model convergence. So this is basically your model actually finding a good answer. There's some theoretical evidence that some quantum machine learning models fail to converge compared to their classical counterparts, and they fall into what's called barren plateaus. I won't go into technical details of what exactly a barren plateau is, but just in case you hear that term, if people are discussing quantum machine learning, it's to do with the models successfully finding a good answer. And yeah, as I've probably mentioned a few too many times, we have a limited number of algorithms because it's such a young field. And a lot of them are just direct, naive adaptations of classical algorithms. And these might not be the best suited. And we want to have more in quantum native algorithms. And these are still being developed. It's a very active field where we're hundreds of published papers are published every week, in fact, in particularly this algorithm and software development. And so I'm really optimistic that we are going to find these algorithms. And because it's a field that has such potential broad applications, because it's an accelerator technology, I think it can be relevant for a huge number of fields anywhere that machine learning is currently used, essentially. Final thing I'll note is a question I think I often get asked is, when is there actually going to be practical advantage? So they vary. Many quantum computing companies claim that somewhere between 2030 and 2035, they'll be able to demonstrate practical quantum advantage. I think this is not unrealistic. I would probably agree with them, but this might not be on all tasks. This might be on a subset of tasks, but this is roughly when people are aiming for at the moment. There's a good recent Outlook paper that I've put on the slide here. So if you've been interested in what I've talked about, but want to go a bit deeper, but still at quite a understandable level for all audiences, then I recommend looking at this paper. Thanks for your attention.
Thank you so much, Caitlin, for the super helpful presentation, and also, for pointing to the additional resource that our audience could look into. And I think there's certainly a lot of hype around quantum machine learning these days. So I really appreciate your insights that really help us separate fact from fiction. I think you touched upon a lot of interesting points. It's helpful to know that there's often a division of labor, so to speak, between classical and quantum computing when it comes to machine learning applications, with each of the fields performing better at certain tasks than others. So I think definitely a lot of food for thoughts. Well, I think we have already some questions raised by the audience. So we can move now to the Q&A segment of the webinar. And so I think there's, well, since you are here, Kaylin, at least you are on my big screen, maybe I will just pick a question that, that is addressed to you. So we have a question from an attendee asking about if including quantum machine, so the attendee is asking if including quantum in machine learning in any way could make the black box problem of AI worse. So alternatively, can quantum actually help us better understand how AI works? So it's just two directions, I believe, whether quantum can make AI more explainable or rather make it worse to explain. Thank you. Over to you, Kaylee.
Yeah, thanks. It's a really good question. And yeah, so explainability is this request from machine learning models to not only provide an answer, but explain how they reach their conclusion. And naively, one could say that it's kind of bad news for quantum machine learning, because if you interrupt a quantum computation and look at what's happening halfway through, you destroy the quantumness. And so it's hard to interrupt and look at what's happening during the computations because of that. So, explainability there maybe suffers. Another thing to say, though, that's on the good news side is that all of the techniques that I know of that have been developed for classical machine learning explainability, ways of interrogating the models, often require a lot of overhead, like repeated runs of the models, for example, to achieve that explainability. Those techniques, in principle, could be applied to the quantum machine learning part as well, because you're just using the same inputs and outputs, for example. And so you might have an advantage there, because if you can run your quantum models faster or more efficiently, then you can basically, the cost of explainability lowers. I will say there is like a nascent field in quantum explainable machine learning. I'm not an expert in it, but this is also definitely something that the field is aware of and looking into.
Thank you so much for the insights. Really interesting to know how quantum integration could impact the explainability issue of AI models. Now, I would like to maybe draw your attention, Stefan, to some of the questions we receive from the audience. I will go in a chronological order. I think there are a lot of questions on quantum sensing in particular. And also I encourage everyone to keep submitting your question via Slido. We are running out of time, but we can still address more questions. So the first question we receive is whether you can explain more about the chip security, the chip cybersecurity dimension that could potentially be enhanced by quantum sensing. So like, how does it work from a hardware or a software perspective? So that's one question, and I hope you don't mind taking another one. We also have another question on if you are aware of any use cases of quantum sensing in weapon development, or maybe just in the military context in general. I believe navigation for sure will have some, impacts on the military applications. So wondering if you have more insight on that. Thank you. Over to you, Stefan.
All right, great. Thank you. Thank you for the questions. So the first one on the chip sensing, the chip security sensing, I mentioned briefly how it could work. As far as I'm aware, it's not a thing that is actually being deployed in practice anywhere right now, but is a sort of a theoretical thing, and maybe there's some proof of concept. There's definitely been proof of concept style experiments, but basically the way it would work is if you had, say, a microchip that was delivered to you by somebody, and rather than just trusting them that they put it together according to your specs and doing whatever standard tests that maybe everybody is already aware what the standard tests are, maybe there's ways to get around them. It's a new kind of test you can do where you have a tiny magnetic sensor that's like a nanoscale sensor. Like, for example, one particular kind of sensor is built using nanoscale pieces of diamond, for instance. And so you can have a little tiny few atoms of diamond, essentially, that are capable of distinguishing, getting down close to the chip and distinguishing between different wires or sections of wires on the chip, which are all very close together. And as the chip runs, you can detect whether current is passing through different parts of the chip, which direction the current is flowing, etc. And in principle, at least, you can use this to see if the chip is operating rogue circuitry, for example. Now, microchips are very complicated, so this is, in practice, this would be a very, probably a difficult thing to really nail down, but at least in principle, it's something that is worth looking into. The second question about weapons. So, well, first of all, yes, the navigation is definitely like what we would call a dual use technology, and we at Sandbox are certainly working with not only commercial sector but also defense entities on this kind of thing. But even within navigation, I mentioned it as like, okay, you're flying around in a plane or whatever. You could do the same kind of thing on, or you could have this similar kind of navigation systems on like missiles, for example, because it's not a manned aircraft, but it's still flying and needs to be very precise in where it's going, and so having more systems to keep track of that is important. And also drones, for example, again, another unmanned aircraft, but very, very important. And the one of the interesting things about drones as opposed to manned aircraft is that they can be designed without having to worry about human usability factors. And so there's a lot of opportunity to do interesting new things with them from a technology point of view.
Thank you so much, Stefan. And I believe we have 2 more questions from the audience for you, but in the interest of time, we will only be able to address one. So we have another question regarding the AI training required for potential security risks and mitigations to ensure navigation and health safety. So I believe these are the use cases you just illustrated, Stefan. So I think the attendee is asking on like what kind of parameters are required to actually train the AI to ensure safety of the users and mitigate the potential security risks. Thank you.
Yeah, that's a good question. As far as the AI side of the sensing story, at least at the sensing story that the sensing applications that we can enable today, the sensors that exist today, the AI side, or generally the computing side of that, is all like a classical computing side, classical data, doesn't involve quantum computers at all. So the data question, the safety question, the training questions, all of those are the same questions you would ask whether or not you were talking about quantum sensing, right? And so the answer is, it's a good question and we need to answer it, but there's nothing special about the answer related to quantum sensing. That's point number one. But indeed, the general thing that one has to do when training any system and ensuring safety is making sure that you've got enough data that it's really a data questions, that you're appropriately unbiased. If I look at the health example for a second, if I'm training this kind of system, I'm collecting a lot of data. In order to train such a system, I need to know something about the background noise I'm trying to screen out. I need to know something about the signal I'm trying to detect and train my system to screen out the things I want to screen out, detect the things I want to detect. And that requires really good, unbiased modeling of the thing I'm trying to detect, and really good, unbiased ground truth data of the thing I'm trying to detect. Just as a quick example, if my ground truth data that I'm anchoring on in, say, the healthcare case happens to only come from one particular segment of the population, but then I intend to use the device on a broader segment of the population, I might have accidentally biased myself toward one particular subset of people, and that'll cause all kinds of problems. But again, that's not a thing that's quantum. That's not a quantum sensing problem. That's a general AI data training problem.
Thank you so much, Stefan. That's really interesting to know. And well, Caitlin, I have one more question for you before we wrap up. And I hope our attendees wouldn't mind us overrunning for a couple of minutes. So just in 1 minute, very briefly, could you tell us about, how you envision the development of quantum machine learning in the next 10 years? Do you actually anticipate something like a ChatGPT moment for quantum machine learning? Thank you.
Yeah, thanks. I would say if we look at the kind of very recent history of quantum computing, in about the last 5 to 6 years, there have been a major hardware and or software developments announced roughly every 2 years. Which is kind of keeping up with the roadmaps of these large quantum computing companies that are publishing them. So I don't think that this 5-year target is unrealistic for some kind of advantage, actually, because basically the progress is being made on a pretty rapid scale. For quantum machine learning specifically, I foresee something that's a bit more similar to something like the development of genome sequencing, where it was firstly used in the scientific realm, where there were major discoveries that, because it was quite a high cost procedure to do at scale. But then the technology became cheaper and more widespread, and now we see that genome sequencing is used much more broadly. I think I would see something more like that, where you have important, but let's say more specifically scientific discoveries first, before then it spreads out across to be ubiquitously used.
Thank you so much, Caitlin. So it has been a really fascinating discussion today, but we will need to wrap up now. So I think today we have heard about, the reinforcing roles played by both quantum and AI. If I can say, they are truly a power couple, and they really have the potential to unlock innovations that would, unimaginable with either field alone. So a lot of food for thought, definitely for us in the international security community. I would like to extend my thanks to our speakers, Stefan and Kaylin, today for your very valuable insights, as well as our colleague Edward for his amazing support with the event logistics. I would also like to thank the donors of the Security and Technology Program, the Czech Republic, Germany, Italy, the Netherlands, Norway, Switzerland, and Microsoft for their support that has made our activities, including the event today, possible. So thank you as well to the audience for attending today's session. Hope to see you on the 18th of November. So in 2 weeks, it's the same time on the Tuesday for the second session of the webinar series, where we will look more closely at what this development could actually mean for the security and defense context. So with that, I wish you all a wonderful rest of your day. Thank you and goodbye.